Good. So my name's Sam, and like this person said here, I'm a developer advocate at GitHub. What that means really varies from company to company. For me personally, it means that all of my development is now in my free time for projects I care about rather than for a company, which is kind of cool. And I'm doing other stuff for my day job. I joined GitHub only a couple of months ago as part of an acquisition of my company, which is still kind of exists, called Semel. And before I was a developer advocate, I was the lead developer for LGTM.com, which is bringing Semel's tools to open source projects. And I started that in about 2014 and was a developer for 3.5 years there. And today, my passions include open source, security, privacy, cryptography. For a little while, I was one of the contributors to the Signal's Android and desktop clients. I'm also super interested in vulnerability research, code quality, and lighting. Most of my projects on GitHub are actually like lighting control and synchronization with music, that sort of stuff. That's my Twitter and GitHub handles. They'll be on all of the slides in case you want to take any pictures for your own, for yourself. So before I start, I'm interested in knowing kind of the distribution of different expertise in the room. So raise your hands if you're involved in software development as a developer or maybe an application security team or your company creates software. Cool, good number. Raise your hand if you're an independent security researcher. Maybe you go for bug bounties, that sort of thing. Okay, couple, cool. Raise your hand if you work for a security consultancy. A few of those. Cool, all right, pretty good, good mix. So today I'm going to start off with a short story. It's a story of many bugs, and it begins on the 7th of September, 2017, when my colleague Mo discovered a vulnerability in the Pivotal Spring framework, and he privately disclosed it to Pivotal. Now, the nature of this bug took advantage of something called the Spring expression language, which allows you to describe sort of Java accesses using a string. Now, it's mostly intended to be used as an internal tool for the framework itself. But with this particular bug, there was data from HTTP requests that flowed to one of these strings, and you could actually do arbitrary remote code execution on certain configurations of the Spring framework. So we reported the bug, and a little while later, the 21st of September, Pivotal made a public announcement where they had patched the bug and recommended that everyone updates. So when Mo actually had a look at the announcement and the patch, he discovered it wasn't actually complete. They were still making the same mistake somewhere slightly different. So he created a new POC that took advantage of the new code path and sent that to Pivotal. A little while later, Pivotal made a patch, but they didn't make it public yet. They wanted to double check that they got it right this time. So they sent it to Mo, and the next day he sent them a new POC. It was still vulnerable. They, at this point, realized that this approach that they were taking wasn't really working. So they took some time to actually refactor that part of the codebase completely to completely remove that type of vulnerability. And on the 25th of October, published that refactoring again, recommending everyone to update. Now, a good thing for Mo is he got a couple more than just one CV out of this, so that's kind of cool. I'm going to talk about a slightly different story. This one's about Apache struts. So similar to similar to Pivotal Spring, Apache struts has this language called OGNL, which allows you to, using strings, describe accesses to Java objects. And if you can execute an arbitrary OGNL string, then you can have remote code execution on a Apache Strut server. Now, on the 27th of April, 2016, there was a vulnerability where HTTP data flowed to an OGNL string and allowed remote code execution. So this was announced and patched and fixed, as you would expect. Then on the 12th of May of 2016, someone discovered a different vulnerability where user data was flowing from a HTTP request to an OGNL string and allowed remote code execution. So they patched it and they fixed it. 20th of June 2016, Another remote code execution interpreting user data as an OGNL string. 19th of March 2017, interpreting user data as an OGNL string. And then again on the 22nd of September 2017, and then on the 24th of September. So there's also only a limited amount of space I have on the slide, so I haven't actually included all of them. And there are another 10 CVEs that are all the same vulnerability, interpreting user data from a HTTP request as an OGNL string, allowing for remote code execution. So we have a little bit of a problem here. And it might seem like I'm just making fun of these two open source projects in particular, but these kinds of stories are common across the entire industry in open source and closed source software. And it's not just small companies either. So for example, Apple published the source code for a part of macOS and OS X called the XNU kernel, which is understandably a core part of it. And Kevin Backhouse, one of my other coworkers, found a vulnerability in a component called the packet mangler. So he sent the vulnerability report to Apple with a POC. They fixed the vulnerability. They pushed out an update. When they later published the source code, because Apple has a delayed publishing of their source code after they've actually released the binaries, Kevin discovered that there was still a bug in the same block of code that they had patched. So he sent them a new exploit that triggered that vulnerability, and then they had to later fix that in a later release. So, we're seeing the same sorts of mistakes being made over and over again, leading to vulnerabilities manifesting over and over again. And if you remember from Eduardo's talk this morning, he included some statistics that Katie Mazouris previously shared about the number of non-spam bug reports that Microsoft gets, somewhere in the order of hundreds of thousands a year. How many of those do you think, not just duplicates, but instances of the same mistake being made throughout Microsoft's software portfolio? And I'm willing to bet that it's quite a lot, and that Microsoft would save themselves a lot of effort, if they could reduce that number. So how do we solve this problem? Could we potentially use information of a new vulnerability as we discover it as an opportunity instead? Once you've found the root cause of a vulnerability, the underlying mistake, could you ask yourself the question, have I made this mistake anywhere else in my software? There could be something architecturally that means that a certain class of vulnerability is more likely to occur in your project. Perhaps your use of C may make you more prone to certain types of memory corruption vulnerabilities. Maybe using things like Apache's OGNL or Spring's expression language might make you more vulnerable to certain types of remote code execution attacks. So you should try and find similar mistakes in your code when you discover one mistake, because the chances are that you will find something. And companies such as Microsoft and Google, who have been actually doing this for quite a while now, call this process variant analysis. So here's a quote from a blog post by Stephen Hunter from the Microsoft Security Response Center. It says, after doing root cause analysis, our next step is variant analysis. Finding and investigating any variants of the vulnerability. It's important that we find all such variants and patch them simultaneously. Otherwise, we bear the risk of these being exploited in the wild. So for them, it's simply not an option not to do it. It's a stage of their vulnerability response process that happens before making details of a vulnerability or patch public, so that they can patch the original vulnerability and all of its variants at the same time. Because if they don't do that, once the patch is released, other people will take it upon themselves to try and find similar vulnerabilities in their code, perhaps reverse engineering if they need to, and if possible, exploit them. So how do you do variant analysis? To be honest, until recently, most of the big players have predominantly been relying on a lot of manual work by their security response teams, focusing on particularly sensitive areas of a code base that are more likely to have vulnerabilities, manually checking how data flows through an application using techniques like control flow or data flow analysis, or like checking the range of values that certain variables can take, ensuring that bounds are checked correctly. All of these sorts of manual investigations often, more often than not, actually need to make use of text search tools like grep and AWK. You can also use IDEs or something else that's also more language aware, like SourceGraph, that allows you to jump to definitions and find references quickly, be able to jump through the call graph, that sort of thing. But as you can imagine, this type of manual analysis is quite difficult. It's repetitive and time-consuming, and it requires a lot of iterative exploration throughout a codebase. Manually checking a codebase as well is prone to human error. So the more complex the mistake you're checking for, or the larger the codebase, or the closer the deadline, the more likely it is that you'll miss something. And it's just not scalable. As the size of the codebase increases, manually checking for a particular class of vulnerability every time that a new one is discovered becomes infeasible. As your list of mistakes need to grow, or as your list of mistakes that you need to look for continue to grow, the list of things you need to check at code review also increases, making the code review process either much slower or inaccurate and insufficient. And on top of that, even in the most high-tech companies, the number of full-time developers far outweigh the number of people working on the security teams. So how can we expect these security teams to actually keep up with all of the code being written by their developers? So what can you do if variant analysis is critical for you, and yet doing so is infeasible? Some of you might already realize this, but we can automate it, right? What if there was a way in which we could describe certain types of coding mistakes that allowed us to automatically find instances of that mistake across an entire code base, using not only like syntactic information about our software, but also including a bunch of semantic information like the call graphs, control flow, data flow. We could then run these checks across our entire code base, run them across multiple code bases, and even run them continuously in the future to guard against repeating the past mistakes that we've made. So it turns out there are actually a few tools already that allow you to do exactly this, and they're definitely increasing in popularity. So Clang Tidy, for example, part of the Clang compiler, can be extended to write rules for C++ that take into account both syntactic and semantic information. Mozilla actually have a custom set of rules that they've written that run against every patch to Firefox that's submitted on Fabricator. And these are rules that every time they come across a new security vulnerability, they're like, all right, can we write a Clang rule for this? And they then go through the effort of actually doing so. And linters as well are starting to include more and more semantic information for their rule sets to use, particularly those that work with statically typed languages. There's also projects like Cosinal, I think, I'm not sure how to say it, for C. And there are a number of technologies emerging that allow you to interactively write queries over source code that include semantic information. Including one solution by my company called CodeQL. You may have heard it before, called SamuelQL. We're actually in the process of renaming it. Now, I'm not going to, in this presentation, directly compare any of these different technologies or tell you why you should use CodeQL over one of the others, but it is my aim to make sure with this presentation to show you why we need tools like this, what they can do for us, and how that might fit into your workflow. Ultimately, I don't really care which tool you use. And I think that, personally, I think that the more alternatives we have, the better, the healthier it is for our ecosystem. And it will ultimately be up to you what you choose. And that being said, CodeQL is the tool that I'm most familiar with, so I'll be using it in my next example. So this example is from the same blog post that I took the quote from earlier from the Microsoft Security Response Center. And it is about Chakra Core, which is the JavaScript engine that powers Edge and a bunch of other Windows applications. So how many people here are familiar with C++2? A decent amount. Okay, I'll pace this somewhat slowly then in that case. So this is C++ code that is part of a built-in function that can be called from within JavaScript. Actually, how many people are familiar with JavaScript as well? A few more. Okay, cool. So this is actually, you can imagine some of the built-in JavaScript methods that you can use that aren't actually implemented in JavaScript. This is an illustration of one of them. And I'll just quickly explain what it does, or the problem with what it does. So this particular function deals with array buffers in JavaScript. And the first thing it does is it gets the pointer to and the size of a particular block of memory that represents a JavaScript array buffer, one that's passed in through the arguments of the function. and it assigns those values to the variables pbuffer and buffer size. After that, this call to var to int may potentially run arbitrary JavaScript code, because the way it works is it actually calls the JavaScript, or the value of property of the past object to calculate its value. And I'll show you some JavaScript in a minute to illustrate that. But with this, given that you're calling back in JavaScript code, you could, for example, override the value of property of the object that you pass in to free the buffer. And then when this code returns, pbuffer would be a dangling pointer. It wouldn't refer to the array anymore. Okay, so at this point, pbuffer is now a dangling pointer. Buffer size refers to the size of the array that the buffer used to be. So then when you later try to perform an operation on this array, using these two variables, you encounter a memory corruption vulnerability. So this is more or less what a JavaScript exploit would look like. And the key bit is they're overriding this value of property, which will be executed when you end up calling that native JavaScript function. So when Microsoft discovered this vulnerability, they assessed it as critical, and they wanted to know if they were making any other similar mistakes in their JavaScript code. In their Chakra core code. So they wrote a query that describes the pattern of assigning a pointer to an array buffer, a pointer to an array buffer to a variable, and then calling back into JavaScript before using the pointer. And this is more or less what the query looked like. I've modified it a little bit to make it fit into one slide. And for anyone that's used a database query language like SQL, there'll be a few familiar concepts here, and I'll just step through and describe what the query is doing. So firstly, we have a from clause here that describes the list of relations that we're looking at. In CodeQL, you produce a database of the code, and then you write queries on top of that database. So we're just looking at tables of data. And in this case, we're looking at the variables in the program, assignments of array buffer pointers, which is something that's defined elsewhere, function calls, and accesses to variables, which is a read or a write to a variable. We then have a where clause that lists some conditions that need to be satisfied, and I'll jump into that in a second. And we have a select clause that lists the columns that we want to output from our query. Jumping into the where condition, this line ensures that the pointer assignment and the variable use are talking about the same variable. So in this case, that's the pbuffer variable, making sure that both the this here and this here refer to the same variable. This next line ensures that there is this function call is a call to a function that might execute JavaScript code. Now, rather than enumerating every single function in the Chakra codebase that could potentially execute JavaScript code, the security researchers knew that any code that calls back into JavaScript eventually uses a function called method call to primitive. So they could simply use the call graph to say that any function that transitively calls method call to primitive may execute JavaScript code. So they might call it directly, or it might call a function that calls method call to primitive, or it might call a function that calls a function that calls method call to primitive, and so on. And that's expressed in this clause here. So yeah, it would be selecting that particular function. This next line says that this call to JavaScript happens after we've assigned the pointer. So firstly, we assign the pointer, then we call this function. And this final clause here says that the usage of the pointer happens after we call back into JavaScript code, which makes sure that the usage there happens afterwards. Now, in this blog post, Stephen Hunter said that this query, in addition to matching the original vulnerability, found 4 additional variants that they also assess as having critical severity. So they were able to patch all of them at the same time and then release them in one patch. So that example was very specific to the Chakra codebase, but there are many kinds of mistakes that are a lot more general. For example, something that's a misuse of a particular language feature, or mistakes that are commonly made with certain APIs or frameworks. And in those cases, you can go one step further and share your queries or your checks with everyone else. Make them open source so that no one has to repeat the same mistake that you do. And beyond that, you can also take advantage of the queries and checks that other security teams are open sourcing, so that you can automatically use that knowledge that they're sharing and augment the expertise of your own team. To demonstrate this, I'm going to go over a slightly different story here. Who's heard of ZipSlip? Cool. That means I get to explain it. Like all cool vulnerabilities, this one had a logo. And it was discovered by the researchers at SNCC. Now, to explain this vulnerability, I need to talk a little bit about how zip files work. Who's familiar with the anatomy of a zip file? Cool, a few people. So you might think that given that a zip file is an archive of a directory of files, that there might be some sort of tree structure inherent in zip files. Unfortunately, you would be mistaken. A zip file is simply a list of entries where each entry has a path string, which actually contains the hierarchical information of the zip file, which is just going to be a bunch of folder names with slashes, etc. Now, there is a lot of code out there that performs unzipping operations, and for a lot of them, what they do is they take the path for each entry as they're going through the zip file and just concatenate it to the destination directory. However, you can have paths that look like this. The laughter recognition there are definitely what I was hoping for. So notably, these have path traversal components, which allow you to go to a parent directory. And when you concatenate this with a particular destination directory, the operating system will resolve these to outside the target directory. If you're unfortunate enough to be running an unzipping program as root, someone could cause a lot of damage if they send you a zip file that's malicious that you then try to extract. Anyone as well that's familiar with Unix file systems knows that the parent of root is root, which means that you could just have a very long string of these and then pretty much guarantee where the file will be unzipped to on the target computer, anywhere you choose, basically. So, SNCC found this out, that lots and lots of applications were making this mistake. So they'd put a very big effort in to try and find as many of them as possible. And they did a big disclosure with like a couple of dozen projects. Now, Microsoft also wanted to know, actually, before I go on that, here's an example of some vulnerable code. And this is the problematic line where you're basically joining the destination directory to the path of the zip file entry. And to prevent the vulnerability, it requires this one line here, or these two lines. And in pretty much every programming language, the fix is about that simple. So it's very worth doing, regardless of what the threat model necessarily is of the application, or whether you're expecting to extract malicious zip files. So Microsoft wanted to know if they were making mistakes like this anywhere in their code. So they wrote a query. This query searched for C# code where data was flowing from zip entry paths to I/O operations without some sort of sanitization step like this along the way. They ran it across their code, found a bunch of results, fixed all the results. But then what they did is they open sourced the query so that other people that had C# code that did any unzipping operations could also automatically check for zip vulnerabilities. And then there are a few more queries written for other languages and other checks that people could run as well. So I may have convinced you at this point of some of the value of doing variant analysis. And I'd like to quickly go over what it might look like if you wanted to do variant analysis and fit it into the workflow for development at your company. This is a simplified model of basically what companies like Microsoft and Google are doing. And I'm going to assume that you already have a workflow in place for responding to vulnerabilities. And if not, we'll go over that in a bit. So you probably have something that looks similar to this. You find out about a new bug, diagnose it to find its root cause, fix the bug, and then deploy the fix to your users. The natural place for variant analysis to fit in would be additional steps after this, after the root cause analysis. Firstly, you would describe the mistake as a query in whichever tool you're using to do this automated variant analysis. You would run this query against your code bases to see what results you get. You'll probably end up with a number of false positives or results that aren't actually vulnerable. So you'll probably want to improve your query until the false positives are at an acceptable level and low enough that you can actually triage them manually and go through each of the results, fixing all of these vulnerabilities that you actually have found that are valid. It would then be at this point, after you've fixed all these variants, that you would then deploy a new version of the code to your users, fixing all of these vulnerabilities at the same time. Beyond this, now that the query is written, you can actually run these queries regularly, continuously monitoring your code for new variants. For example, it could be run periodically or just before a release to make sure that you haven't introduced any new bugs since the last release. Or even better, it could be incorporated into the CI process for your developer's workflow to make sure that all incoming code changes are checked before they get merged. Discovering and fixing them in code review, which is effectively what Mozilla are doing with Clang. The final ideal step beyond this would be to share this query, if it's a general purpose query and it makes sense, as widely as possible. Ideally open sourcing it so that other security researchers or other security teams and development teams can benefit from your research and the mistakes that you've made. And then finally, incorporating the queries and checks that other people are making so that you don't make those same mistakes that they have been. And with this whole process in place, your software will probably have far fewer bugs or far fewer vulnerabilities caused by repeated and easily preventable mistakes. I imagine that that would bring, for example, Microsoft's number of reports down quite a bit. So what about for those of us that don't actually have a security response process? For example, you may be part of a small software startup or working on an open source project. Well, the first thing to understand is that sooner or later, if you are developing software, you are probably going to be faced with a vulnerability that you need to deal with. And it would be good to have an idea of how you would go about dealing with that situation. But in the meantime, until you get your first vulnerability discovery, I would definitely recommend making some form of automated checks part of your workflow by running, security tools that are freely available to run. Automatically analyze your pull requests for things and for things that are already well known and talked about, and take advantage of the knowledge that's already being shared by various security teams. And if you're a security researcher or a consultant, you can actually take advantage of tools like this to find even more vulnerabilities than you already are. You go over past vulnerabilities that you've discovered, maybe write queries or checks for them, see if there are any that you missed, run these queries against other projects that might be applicable. Maybe you could get access to a few more bounties, which is always good. So if you want to get started with variant analysis, how do you do that? Well, I'm not going to recommend that you go ahead again and use GitHub software. That's a choice for you to make. But I do want you to consider what variant analysis could do for you, if that's something that'll work for you, and what tools will help you achieve better security, hopefully reduce the amount of manual work that you're doing. So if you're writing or maintaining software, look at which tools other companies are using, some larger software projects, etc. Try out a different selection, see what works for you. If you're a blue teamer or a security researcher, experiment writing checks or queries with different technologies. It might be that the sorts of vulnerabilities that you're looking into are more easily expressed in one tool over another. And take a look at what other researchers are doing as well. Look at blog posts, look at research, go to talks and stuff. So to recap, you should do variant analysis if you are creating software, that is. Better yet, you should do automated variant analysis. Checks should be run continuously, not once off when a vulnerability is discovered, because there's always a chance you can make that mistake again in the future. use and contribute to open source queries, help other security teams, and use the knowledge that they're sharing. If you are a security researcher, you can use variant analysis as a tool to find many more vulnerabilities and really supercharge your research. And then the last thing I want to say is that variant analysis is not a replacement to things that are already out there. It is very much a complementary, enhancing thing to other things. For example, if you're already using fuzzing a lot in your toolkit, you can then take results or positive results from fuzzing and then write queries for that and then find even more vulnerabilities and prevent it again against entire classes of vulnerabilities. If you're using pen testing or red teaming, that sort of thing, then again, your discoveries that you make with that can be multiplied by when you use variant analysis. That's about all I have time for and all I have. Thank you.
Thank you very much for your talk. We have time for questions.
Do you know of any usage, not as an internal development team, but lifting the intermediate language or using a disassembler to get the code of a closed source binary and use such a tool to?
There are definitely tools that allow you to do a lot of data flow analysis over binaries, that sort of thing. Are you talking about CodeQL specifically, or?
Yeah, to have the same kind of query to be able to do it.
There have been experiments. A lot of the sort of patterns that you look for are stuff that's often lost when something's compiled to binary. Like it might be, you might use certain hints, like the naming of certain functions and stuff that match a certain thing, or usage of certain internal libraries. There's definitely people that have done that and found a bunch of things, but it's not its most common use case.
How would you assess that the external knowledge base doesn't introduce unknown vulnerabilities?
You don't. Quite often and then that's kind of the point of it as well. Like someone creates a new query, that query may reveal something new that you didn't know about in your source code. So you'll want to probably run that to check it and see if you can find anything. Yeah.
More questions? Yep.
Are there some tools that automatically generate queries based on patches and stuff like this?
There are some tools. I think Consonel might do something similar to that, where I'm not sure where it's generated on a patch, but you can definitely describe patterns that also include fixes that can automatically generate patches. So it's kind of the other way around. I'm not sure if there are many tools that will do an analysis of a patch to work out what the vulnerability is. I think quite often with that, you might end up with situations where it's not general enough and will only end up finding just that particular patch and not similar problems. So that's always kind of when you're designing a check, that's always sort of something you need to consider, like how general purpose can I make this? Yeah.
Yep.
So one question, I'm not really familiar, but could you also state an outcome to remove false positives? So not just how to find it, but also, and you should expect by fuzzing whatever you find to have a dangling pointer, for example. So you then could potentially remove the false positives on the search.
So again, for about CodeQL specifically, or so in the past, we've definitely augmented those sorts of results with or we added other relational data to the database that you could then incorporate into queries. I think for doing that, you'd probably want to actually produce the results table and then actually run a second step afterwards, which would be something that CodeQL doesn't specifically do, but you could definitely use CodeQL in that fashion. But I'm not aware of anyone that's actually doing it in that way. I think most of the triaging is actually done manually afterwards.
More questions? I actually have a question myself.
Yep.
So in this like crazy world, we have some companies that are actually running several different releases per day. I'm thinking about DevOps, for example. Does this fit in this kind of?
I definitely think so. You would end up putting that. You'd end up relying on something that you run during the kind of like CI stage rather than kind of during a release. So before, kind of at the same time you do code review, you would run checks. Like, okay, this patch does or doesn't introduce any results, and then act upon it. That's effectively what Google and Microsoft again. They have a lot of very regular patches, and and Mozilla as well. So yeah.
One last question. Okay, thank you very much again.
Thanks.